It's difficult to follow Ben Feringa. I didn't need to say that, you all know it. The subject of my talk is quite different. I was asked to talk about photophysics and future energy. And the work that we do with solar cells is done both places where I have an appointment. One is in Prague in the Czech Republic, and the other one is in Boulder, Colorado. And the collaborators listed here are at both places. And the support is also at both sides of the Atlantic. I've listed here a simple introduction to the subject of singlet fission that has just appeared in the special issue of this year's special issue of Molecular Frontiers journal, in case you are interested in finding out a little more about singlet fission. So, energy. Mankind uses currently something like 15 terawatts or so and this is expected to approximately double by the middle of the century and at least triple or more by the end of the century, primarily because people in the poorer parts of the world are catching up. People in China and India and Indonesia and other countries like that. And this is a very good development. This is what they certainly deserve. But it will demand a considerable increase in the amount of energy that mankind produces. And one has to ask, where will that come from? We have plenty of coal and other fossil fuels. And one might imagine, naively perhaps, that that's good enough. We'll just keep burning them and we'll get all the energy that's needed, at least for centuries. But there is a problem associated with that, as you all know, and that is the release of additional carbon dioxide into the atmosphere, which causes a warming up of the biosphere, of the surface of the Earth. The usual explanation that's given in newspapers and other places is that the light that comes from the sun passes through the atmosphere with little loss and reaches the surface of the Earth and warms it up. The surface of the Earth emits radiation whose intensity peaks at much lower energies because it's not as hot as the sun. And that infrared radiation is largely absorbed by the atmosphere and returned to the surface, and so it's sort of trapped and increases the temperature of the surface. The reason for the trapping is primarily water, but some of it is also due to carbon dioxide. And so the argument is, as we put in more carbon dioxide, we'll have more of the trapping. This is believed by scientists, but it is not believed by all politicians, some of them influential politicians. And some of the arguments that are given against that explanation are ludicrous, and some of them have a semblance of scientific reasoning in them. For example, one can say, well, we already have enough carbon dioxide in the atmosphere that it absorbs pretty much all that can be absorbed of the infrared radiation coming from the surface of the Earth. So why will it matter if we put in more? And so that simple explanation isn't actually accurate enough. What really happens is known to scientists as positive radiation forcing, and somewhere I think there is a No. Ben, did you keep the... We see with friends like this, you don't need enemies. Your laptop is... Oh, that must be the one I threw out.
Yeah, there is a purpose in that.
But maybe I can make this work. Can you see this green spot? Okay, I'll use this one. And forget about your computer. You'll buy another one. So what really happens is that with an increase of CO2 in the atmosphere, the IR radiation is getting absorbed closer to the surface of the Earth. And so the top of the atmosphere doesn't get as warm as it would with less carbon dioxide. And it's the top of the atmosphere that determines the amount of radiation that's emitted into the universe. Just like the radiation coming from the sun is dictated by the surface temperature of the sun, a little over 5,000 degrees, not by the internal temperature, which is much higher. So if the Earth radiates less of that IR radiation into the universe, well, it will get warmer on the surface until a steady state is established again. So there are many of these spurious arguments. I actually spend my time in two countries. In the United States, where half of the voters vote for a party that claims there is no such thing as man-caused climate change. And the other part of my time in a country that, until not so long ago, had a president who wrote books about the fact that climate change is only an invention by scientists who want to get more funding. So it is important for the general public to be sufficiently educated about what is actually going on. And we had a wonderful lecture about this yesterday, so I don't want to elaborate too much. I will show you some of the slides I prepared for this occasion. Some of them you've actually already seen. This is the top of the Kilimanjaro, and this is what it used to look like. This is what it looks like now. It's the difference of only 7 years. When I climbed the Kilimanjaro back in the 70s, there was a whole lot more ice. This picture you saw, this is what's happening to the Arctic ice. This picture you also saw. This is a list of results, less anecdotal than what I showed so far, of a real statistical treatment of observations of temperature anomalies that have been measured in the Northern Hemisphere, using all observation stations on top and just some of them at the bottom, but the results really look the same. What was normal in the years 1951 to 1980 is shown here. The average is called 0, and then there were these anomalies, either in the positive side to warmer temperatures or to colder temperatures on the left. And in this graph, it was divided equally, 1 to 1 to 1, 1/3 for each. And as time went on, you see that what used to be the normal average is moving to the left. There are very few of these cold anomalies and a whole lot of hot anomalies or extremely hot anomalies. This evidence cannot really be ignored, although unfortunately, frequently it is. The consequences of what will happen if we do not prevent a further increase of the CO2 concentration in the atmosphere are shown in this paper here by Stocker. What it shows is what will happen as a function of the date shown horizontally at which we finally start reducing instead of increasing CO2 emissions as we're doing now. So if we don't do anything until 2020, we are at this line. If we don't do anything until 2040, we are at that line, and so on. And what these individual lines show is a dependence on how much we reduce emissions per year. If we only reduce by 2%, we'd be at this line. If we do it by 4%, it's at that line. 10% is up here. And so here we show what happens to the amount of warming increase over what we had in the past as a function of these two parameters. You can see if we start immediately and we reduce by 6% every year, we'll have an increase of 1.5 degrees. But if we wait until later, we would have to reduce by much more to get 1.5. If we reduce by 10%, we'd have, and start at 2030 roughly, we already have 2 degrees increase. And the longer we wait, the worse it will become. If we don't do anything at all, 0% reduction, you get up at the end of the century, you have a 10 degrees increase. And the consequences of this, I think we all know about. So clearly, we need a source of energy that is abundant enough and cheap enough and does not increase the amount of CO2 in the atmosphere. And here is a list of the candidates for sustainable energy sources. Now, maybe we'll be lucky and something like fusion will actually work out, although the chances for that are not very good. It has been said to be within 30 to 50 years of success for the last half century or more, and it's still as far from success as far as we can tell as it was half a century ago. But if we just look at the ways of generating energy that are sustainable and that we already know work, we can look at wind, and estimates are that something like 3 terawatts would be extractable. Tides and ocean currents, a similar amount. Geothermal energy, hydroelectric energy, much of that is already actually used. Biomass, shown here. But all of these pale relative to solar energy. Something like 600 terawatts, 100 times more than any one of these others, appear to be practical. Of course, the total amount of solar energy that hits the surface is 120,000 terawatts. But most of that we cannot touch, we cannot really use. But even if we just used a small fraction of what is practical, we could easily solve the problem that has been mentioned, the increase in the energy consumption that's coming. Well, so how does the solar energy get converted into electricity? You may have all seen this picture, but perhaps some of you have not. This is an example of how a silicon cell works. You have a junction where silicon that's p-doped and silicon that is n-doped touch. And at that point, the diagram of the energies of the electrons that are the least bound, that would be this line, and those levels that can be occupied but are normally not in the dark, are shown here. The distance between them is the so-called band gap. If you send in a photon that has less energy than the band gap, it won't get absorbed. If you send in a photon that's exactly the energy of the band gap, well, then it will generate a hole in the highest occupied levels, and it will place that electron that's been excited at the bottom of the conduction level. Most photons, of course, if they are absorbed, will not have exactly that energy. the sun is not monochromatic, it will have, usually they will have more energy. So an electron will be taken from somewhere here, a hole will result there, and the electron will end up somewhere there. But they will very rapidly return to the bottom of the conduction layer or the top of the valence band. And so this amount of energy is going to be converted into heat. This amount of energy is going to be converted into heat. You will end up with the same situation as if your photon only had this much energy. Now, the electrons that have been excited will move downhill over here. The holes that have been excited will move over here. You'll end up with a voltage that's defined by the difference of these two layers. And that's the useful voltage for electricity that you can actually use. For each photon, you will get one electron-hole pair, and the result will be a product of the current and the voltage difference that you gain. If you increase the size of the band gap, you will increase the voltage, and that's good, but you will have a smaller number of photons that are absorbed because now many of them will no longer have the energy to make it from here to here. As a result then, in an article that was published back in the early 60s, we have what's known as the Shockley-Queisser limit. That's a theoretical limit of the efficiency of a solar cell that only has one junction, and it's about 1/3. Now, I discussed this once with Professor Queisser. He told me they had a hard time getting this article published. The editor wrote back saying, well, you know, the reviewers don't find anything incorrect in what you want to publish. They just tell me that it's totally useless. Well, that article is now one of the most quoted ever in that journal. And I'm mentioning this because there are a lot of young people here, and I think you should not get discouraged when your papers are rejected and you are told that they are of no interest or things like that. Persist. You may end up being the most quoted author in that journal. So this is what the energy diagram looks like. What the cell actually looks like in practice is more like this, where you have the two layers, the N-type semiconductor layer and the P-type semiconductor layer, and they are protected on both the top and the bottom. There are contacts in the back and in the front where the light comes from, and the contacts collect the electricity that's produced, and you can then use it. I show here one bulb. That's a 100-watt bulb. That's what you would get if the efficiency of your cell were 10%. Now, I said the maximum you could expect would be 1/3, 32%, but one is not far from that. In the currently really best single junction cells that are very cheap, you get something like 25%. Well, that's not far from 32. Still, the number may appear to be rather low and somewhat disappointing. Why isn't it higher? Well, I have already actually explained why it is not higher. That was the Shockley-Queisser article. If you try to plot the efficiency under sort of standard conditions, as a function of the band gap that I mentioned, there's a maximum here. If you have a smaller band gap, the voltage that you're getting is just too small. If you have a bigger band gap, then the fraction of photons that get absorbed is too small. And so this is the optimum, about 1/3. There's a couple of notes that I have here. One of them has to do with the fact that sunlight is a commodity that's not constant in time. At night, there is not much of it. In parts of the world close to the poles, maybe for months, there is none of it. So storage, batteries and other types of storage, is an essential component of trying to generate electricity from sunlight. Another point is that one does not need to generate electricity. One could go directly to reducing, say, CO2 to make fuels, the so-called solar fuels. That is a technology that has not really been worked out yet, but people are working on it. Oh, lots of people are working on batteries as well. So these things one has to keep in mind. Now, this is what the solar light distribution looks like. The curve that I show here in a full solid line is the black body radiation predicted by theory for an object that has the temperature of the surface of the sun. What actually makes it through the atmosphere is less, particularly in the UV region, where ozone removes by absorption much of the radiation. And that's just as well, because otherwise we would all suffer from skin cancer and similar problems. There are also other regions in the spectrum that are eaten out by absorption by species present in the atmosphere. And that's why what you actually get at the surface of the sea level is a substantially reduced amount of energy. Now, if we use silicon, for example, then the band gap is approximately at this wavelength here. And so all the photons that are on the right are lost. They are just not absorbed at all. And the ones that have more energy than the band gap, which is here, so it's these photons, act as if they only had this much energy. So the rest is lost as well. One can, of course, build more complicated cells. If you are going to use a solar cell on a probe that you're sending to Mars or maybe a satellite around the Earth, you don't mind paying $100,000 per square meter. And then you can do better. How would you do that? Well, you would have a combination of several junctions, not just one. So you would have one junction that would have a band gap here, and another one that has a band gap there, and a third one that has a band gap here. You first absorb the photons of high energy and generate high voltage. Then you, in the next layer, you will absorb the photons that have lower energy, and you get lower voltage, and then finally the last ones. And if you build a cell like that, it will look roughly this way. Here's the various junctions. There's one at the bottom, one here, one here. But you have to make sure that the current that flows through is the same everywhere, because the current will have to go from the top and the bottom. And doing that is possible, but it's extremely expensive. And this is not the kind of cell, even though it has nice efficiency, 40%, it's not the kind of cell you can put on roofs on every building in Sweden or anywhere else. You can use them on very special occasions. What singlet fission does is consider this again, but in a way that does not throw out the extra energy that most of the photons have because they are above the band gap, but uses it to make more than one electron-hole pair from one photon. And the result is shown here. It's the red curve instead of the blue curve. Now, you are not at 1/3 maximum, but close to 1/2 at maximum. Now, this is the maximum theoretical efficiency you would get with a singlet fission cell. It would contain first a layer that has the ability to do singlet fission and takes care of the photons that have high energy, and that will be followed by a layer that uses ordinary material that produces one electron-hole pair from each photon, and you would not have any requirements for matching any current. So this could still be a cheap cell. Now, I haven't really said what singlet fission is, but here it is shown. You have an absorption of a single photon, that's process 1, and it occurs in a molecular solid, maybe a tetracene or pentacene or something like that. And in the step of actual singlet fission, the molecule that was excited into its singlet state by that photon shares half of its energy with a neighbor molecule that was in a ground state. And they both end up in their respective triplet states. So one could write a little chemical equation saying that an excited singlet molecule plus a ground state molecule will produce a pair of triplet molecules that are next to each other and they are coupled into an overall singlet. And this is actually reversible. And then the process continues in that the singlet state develops in time into a quintet, and probably, this has not yet really been proven, into a triplet. And then finally, the two triplets separate. They go their own independent way. They lose the spin coherence. And if they both arrive at a junction of the kind we talked about, they each produce an electron-hole pair. Well, this suggests immediately that there will not be very many materials that will do singlet fission efficiently, because there are not very many materials where this energy difference is the same as that energy difference, and both are half of the original energy difference. Actually, the reason we don't have singlet fission cells on the shelves in supermarkets is that the materials that are known to do this efficiently, 200% yield of triplets, are very few, and most of them are not suitable for actual practical use because they will not last for an hour or two on the roof, let alone for a year or two. So this has to do, this is a repeat. You see here the part of the spectrum that would be taken care of by singlet fission, then there would be part that is treated by ordinary material, and that would give you together that red curve that you saw. Now, how do we know that singlet fission actually takes place in some materials? This material here, diphenylisobenzofuran, is one that we proposed and sort of developed. And what I show here is a bit of spectroscopy. If you take a layer of this material, thin layer, and you measure its absorption spectrum, it is shown here with the dotted line. So that tells you immediately that this is a nice molecule for the laboratory, but nothing that we will ever be putting on our roofs, because the absorption does not start until quite high energies. If you hit this sample with a very short pulse of UV light at this energy here, the scale is in thousands of wave numbers, then you generate excited state, singlet, that I claim produces the two triplets, and the spectrum changes a bit. You will now see the absorption that's due to the triplet. It looks very much like the absorption of triplet that's produced in solution. And also you see a bleach of the ground state absorption. You can analyze this as a function of time shown here. You see we're talking about quite short times. This is in femtoseconds. That's 10 to the minus 15th of a second. We can analyze the spectra, extract from them the concentration of the triplet, or the amount of the triplet at any one time. Here is a function of time, 200 picoseconds is the whole scale. And we can also extract something quite interesting, which is the concentration of the ground state molecules. So it's shown in the inset. Again, 200 picoseconds total. Initially, you see a rapid drop by a certain amount. Well, that is a disappearance of the ground state molecules that have absorbed a photon. That's very, very short because the pulse with which we're exciting is very short. But then that is followed by further disappearance of more ground state molecules. And if this amount, if this distance is the same as that, then you could say that the number of molecules that disappeared in the second event is the same as the number of molecules that were initially excited. And this is actually due to the singlet fission, because in the singlet fission, an excited molecule gives energy to the ground state molecule, and therefore the ground state molecule disappears from the spectrum. You can see it disappear. The time constant in this case is something like 25 picoseconds. The yield at room temperature for a layer of this molecule is about 140% instead of the ideal 200. At lower temperatures, it is actually within the experimental error of 200%. So this molecule is reasonably effective. But that's not enough for any practical use. I have listed here some of the conditions, the most important ones, that a real practical solar cell material would have to satisfy. And having a good yield, 200% yield of that triplet, is obviously the first one. But there are many others that I don't want to go through in any detail, ending with the fairly obvious ones, like reasonably low cost, sturdiness under conditions of use, lack of toxicity, and so on. Now, we have two questions then. If we want to come up with materials that will be useful, they have to have some molecular structure, that would be the nature of the chromophore that's used. And second, they have to be put next to each other in the solid in some way that makes them effectively produce the singlet fission events rapidly. If they are slow, then other events, other decays of the excited state will prevail, and you will never get close to the 200% yield of the triplet that you want. Now, back in 13 years ago, we published a paper in which we pointed out that the choice of the chromophore is actually relatively straightforward. We wanted singlet fission to be isoergic or maybe slightly exoergic to meet the requirements that I listed about the triplet being halfway between the ground state and the excited singlet state. And you can get there not by going through lists of results published in catalogs and reviews, because very few molecules actually satisfy that requirement, but by thinking about the nature of the problem. If you had an ordinary molecule, such as H2 molecule, that's an example that I've chosen here, not only because we can calculate the energies of those states accurately, but also because of its simplicity, you will generally find that the distance from S0 to T1, from the ground state to the first triplet state, is much bigger than the distance from the triplet state to the excited singlet state. So this would not work. There would not be enough energy in the S1 state to make two T1 states. If you dissociate the hydrogen molecule, make the distance infinite, you will end up with two hydrogen atoms, and then, of course, the triplet will have the same energy as the singlet. So the distance here will be 0 between these two curves. The excited singlet will be quite a bit higher. Well, this is not what we want either. But the curves are continuous. So somewhere in between, you will meet the condition that this distance is the same as that distance. So you don't want an ordinary molecule. You don't want a perfect biradical. You want something in between, something that people usually call a biradicaloid. And I indicate that here for the H2 molecule and also for the ethylene molecule, where you can do something similar, not by dissociating, but by twisting. And if the molecule is 90-degree twisted, the singlet and the triplet have almost exactly the same energy. That would be like that situation that we had with hydrogen. And if they are untwisted, these two are almost the same. Now, ethylene would not be a good absorber for a solar cell because it only absorbs in the vacuum UV. But we can manipulate the energies of excitation in a way that I'll show on the following slide, and also in the way that's shown here. This shows how we came up with this molecule of diphenylisobenzofuran by starting with a perfect biradical that would be like being over here, and then modifying it by bringing in enough interaction to make it sort of halfway a normal molecule, ending up here. This is actually a molecule that you can buy from Aldrich, and that's the one we made measurements on. So this concept actually works. This is just a very brief mention of how you can change the position of the, or the size of the band gap. This is ethylene itself. We just looked at that. I said it absorbed at energies that are too high. The distance from the highest occupied molecular orbital to the lowest free molecular orbital is 2 energy units. It's huge. But you can modify that by putting a donor and an acceptor at each end. What that does is changes the nature of conjugation in the system, and if you choose a strength for the donor and the acceptor to be the same, then you have a very simple formula telling you how much you've reduced from the original value of 2 to a smaller value. And you can also plot it as a function of that parameter d, and you can see you can go all the way to 0. This is what you do in the so-called captodatively modified biradicaloids. Indigo is one of them. Now, indigo is blue. That's the color of your blue jeans. And that could be used in principle. It indeed satisfies the properties that we want. The energy of the excitation for singlet is twice the energy of the excitation of triplet. But we cannot use it because there is a photochemical process in the excited state that's fast, and the molecules decay to the ground state very rapidly. Now, we've modified that molecule and started to look at CIBALACKROT, which is shown here. And that does not suffer from this problem. It has another problem. This is what the crystal structure of 2 different modifications of CIBALACKROT looks like. And you can see here that the molecules are parallel, and that's true in both of these modifications. The separation is slightly different in each. And what happens instead of singlet fission is charge transfer. One of these molecules gives an electron to the other one. They form a charge transfer state, and that partly goes on to triplets, but most of it decays. And so we don't get more than 100% efficiency. So this is how nature defeated us in this particular case. There are many ways in which nature has defeated us. In many cases, I'm not going to tell you about all of them. This I will not go through in any detail. It just shows the complexity of the whole process. This is indicating 2 molecules, A and molecule B, which are in a state that's shown in red, but potentially could be in other states which are also listed in black. So we start with 2 molecules in solution, for example, both in the ground state. One of them absorbs photon, so it is in S1 state, excited singlet. The other one is still in the ground state. If they meet in an encounter complex, they can produce a set of states that are a mixture of 2 states, a mixture of the one molecule, the B excited, or the A excited. This is known as the exciton. And then they can undergo singlet fission to actually produce the state in which both are in the triplet. The way they do that is through the intermediacy of this charge transfer state in which that I mentioned already, in which you have one molecule as a radical cation, one as the radical anion. This could be a real state. It could also just be a virtual state that cannot be observed. And then you have additional steps until finally you have the 2 triplets. This is this is a complicated scheme that provides many opportunities for decay to the ground state. And that reduces then the efficiency of the whole process. In a solid, you start with the molecules already being together. You don't have to wait for any diffusion, but otherwise it's similar. So you can, from the exciton, you can get the molecules to move together, form an excimer that stabilize so much that then it no longer wants to go to two triplets. Instead, it decays to the ground state, or maybe fluoresces. These states, the charge transfer states, could be actually so stabilized that one of them forms. That's what happened in CIBALACKROT, as I mentioned to you. And you could also make the two triplets. They could decay to the ground state. So you have to worry about two things. One, making the singlet fission very fast. But two, making all the other processes very slow. And this is a relatively difficult job. One sets up the mathematics associated with all the configurations that are in play. I'm not going to go through that in any detail. The mathematics become, we simplify them. They become very simple if you just work with two ethylenes as an example. And I can tell you that there you can actually state a rule about the packing of the molecules that you want to optimize the singlet fission rate. It's a very simple formula. It's some constants multiplied by a square of the difference of two products. One is the product of the red overlaps, this atomic orbital overlapping with that one, and this one, same one, overlapping with the other one on the bottom ethylene. And that would be one of these. And the other one is a product that's shown in blue. Again, product of two overlaps. Well, if the two ethylenes are exactly stacked, these two will cancel when you take the difference and you get zero. What the rule then says that you want one of these orbitals to overlap with both on the other ethylene, and the other one not to have any overlap at all, as would be in this geometry or that geometry, or at most one, as would be at that geometry. So one can formulate simple rules, not only for ethylene, but also for more complicated molecules. And then for molecules that are more complicated, the formulas are a little more complicated, but simple enough that you can actually do calculations for billions of geometries in a few hours on a modern computer. That allows you to find all the optimal geometries for the speed of singlet fission, because you have results not only for the interaction matrix elements, but also for the bad stabilization of the excimer or exciton type that would interfere. And so for the molecule I talked about, the diphenylizobenzofurane, this is the best geometry you could have. This is the next best geometry, and so on. And we have similar results for other molecules as well. These are the results for CIBALACKROT. So even for a quite large molecule, you can do this calculation easily. These are the results for TETRACENE. This is what would be the best arrangement, the next best arrangement, and so on. So we can make predictions about this, and then we can try to synthesize the structures that are shown as optimal here, either by crystal engineering or by making a covalent dimer, and then using that as a solid material. There is one catch that I need to mention, at least briefly at the end, and that is that there is reason to believe that the consideration of two molecules at a time, as most people have been doing, is actually not enough. At least in some cases, there are effects on singlet fission that are due to more distant molecules. We think you have to consider at least three and maybe more at the same time. And this is illustrated by these two forms of the diphenylizobenzofurane that I've been talking about. This is one crystal form, this is another. This one is very good in singlet fission, and I gave you the numbers. This one is at least 10 times worse. You get very little triplet. And yet they have the same structure when it comes to neighbors only. If you look at any one molecule and its neighbors, it's basically identical in both crystal forms. It's only the relation to the next nearest neighbors that is different here and here. And that's shown in these two bottoms. So that's a final word of warning. We are still only a fraction of the way toward a singlet fission system that would actually deliver the promise that the theory suggests is there. So singlet fission works in principle, but the devil is in the details. Well, I'd like to end by thanking you very much for your kind attention and the organizers for the invitation. Thank you.